All right, so welcome to this 9th lecture in this course on algebraic topology. We're at the University of New South Wales, and I'm Norman Wildberger. So last time we talked about polyhedra. It was an introduction. We talked about very simple, basic, familiar objects, and we introduced and proved Euler's formula relating the number of vertices, edges, and faces of a polyhedron that basically has the shape of a sphere. So today I'm going to talk about some applications of that very important formula, and I'm going to introduce some more sophisticated polytopes, or polyhedra, perhaps some more interesting ones, and we'll even venture a little bit into higher dimensions briefly. And then we'll switch gears and talk about another way of thinking about Euler's formula relating to graphs. All right, so let me start today by applying Euler's formula to the statement that there are really 5 Platonic solids. So the theorem is there are at most 5 Platonic solids. And our proof is going to use Euler's formula. And so we're going to assume that we have a regular polyhedron, or polytope, we can also say, with n, the number of edges on each face. So we're assuming that all the faces are polygons with the same number of edges. We're calling that number n. And we'll assume that the number of edges that meet at a vertex is m. So m is the number of edges that meet at a vertex. And otherwise, we just have some polytope, which is the general shape of a sphere, so that we know that Euler's formula applies. Okay, we're going to do some counting now. We're going to count edges. So we'll say that the number of edges is the number of faces, which is f, times n, because there are n edges per face. And that counts each of the edges twice, so we have to divide by 2. So we're counting edges in terms of faces. And now we're going to count vertices, v. So every face has n vertices, but then we're counting the vertices too many times. Then a given vertex will be counted m times, because it will belong to m faces. Because there are m edges meeting at every vertex, also m faces meeting at every vertex. So we have to divide this by m. Okay, so we're counting the vertices by saying it's the number of faces times n vertices per face. And then we have to divide by m because m faces meet at every vertex. Okay, so now we can introduce Euler's celebrated formula, v minus e plus f equals 2. And we're just going to plug these values in. So we get f times n over m, that's the number of v, minus f times n over 2, plus, well, f equals 2. And so f times n over m minus n over 2 plus 1 equals 2. And if we get a common denominator, we can rewrite this as f equals 4m over 2n minus mn n plus 2m. So I'm just taking a common denominator here and then rearranging to solve for f. And so we conclude that we must have that the denominator here, 2n minus mn plus 2m, that better be bigger than 0, because we do want a positive number of edges, certainly. And we can rewrite that as 2 times n plus m is bigger than n times m. That's a nice inequality that has to be satisfied between these two numbers n and m. All right, we can rearrange this just a little bit if we write this out as 2n is bigger than m times n minus 2. And if we remember that, well, our numbers m and n have to be at least 3 because we want our polytopes to have at least 3 sides. And we want at least 3 faces meeting at any vertex. So their natural number is bigger than or equal to 3. In particular, n minus 2 is positive. So if we divide by that, we'll get 2n over n minus 2 is bigger than m. And m is bigger than or equal to 3. And that tells us then that 2n is bigger than 3n minus 6. Which tells us that n is less than 6. Okay. So what have I done here? I've just taken 2n over n minus 2 is bigger than 3, so I've just multiplied by n minus 2, and then I've just rearranged the 2n over there, the 6 over there, and we get n is less than 6. And now this equation is symmetrical in n and m. They're playing exactly the same role. So also m, okay, or 6 is bigger than m. And then there's only a finite number of possibilities. Each of these numbers has got to be either 3, 4, or 5. And so the possibilities are for n and m, they can be either 3, 3, 3, 4, 3, 5, 4, 3, or 5, 3. Those are the only pairs you can check that satisfy this inequality. And we are getting the, that's the tetrahedron, that's the octahedron, that's the icosahedron, that's the cube, and that's the dodecahedron. This proof actually shows something more, because we actually haven't really used the fact that the faces had to be geometrically regular. All what we use is that they had to be combinatorially regular. So that means if you consider the somewhat more general problem of just taking a sphere and divide it up into a regular complex, but not necessarily geometrically so. So for example, you might want to try to use squares to cover the sphere, and maybe 3 squares or whatever, or however many squares you decide. That's not a square. So even if you allow yourself bent shapes, as long as they're topologically regular polygons, the only way of doing that is essentially using the 5 Platonic solids as one of your basic blueprints. There are no other ways of creating a regular pattern on the sphere. And I also show that it doesn't actually show that there are 5 Platonic solids. The construction of the Platonic solids it still has to be done separately, as I mentioned the last time. All right, let me give you a problem to think about. Problem 11. So a soccer ball is made of pentagons and hexagons with three meeting at each at a vertex.
3 faces.
Three of the faces meeting at a vertex. Show that the number of pentagons must be 12. And I'll call that A and I'll call this B. This is a start problem, a little bit harder problem. So the start problem is only for honor students or people aspiring to that elevated level. So this is a harder problem. Is what are the possibilities for the number of hexagons? Okay, I now want to talk a little bit about some other.
Do you have to have at least 1 pentagon and 1 hexagon?
Sorry?
Do you have to have at least 1 pentagon and 1 hexagon?
No. You could try making it out of hexagons, but the problem says that you won't be able to. Okay, so other polyhedra. So I'll just mention a few of them. You can, perhaps if you're interested in, you can go away and investigate them. There's an interesting class of things called Catalan solids. These are the duals of the Archimedean solids. The duals of the Archimedean solids. So I remind you, the Archimedean solids had the property that all the vertices look the same. So we take the centers of the faces of an Archimedean solid, you get a Catalan solid, and their faces are all going to look the same. But their vertices and edges won't. There's another, a rather very broad class of solids called the Johnson solids or polytopes. And these were only written down, I think, in the 60s. There's 92 convex polytopes whose faces are all regular polygons, but possibly different types of regular polygons. Equilateral triangles, squares, regular pentagons. You can use whatever you want as long as they're regular polygons, and you have to make a convex polytope. Of course, the Platonic solids and Archimedean solids, and they fit into this category, but there are others as well. Another interesting family are the, I think it's called deltahedrons. These are solids made only of equilateral triangles. Polytopes with equilateral triangle faces. I've brought a few along. That's a deltahedron with 14 sides, and that's one with 12 sides. You already know some. You know that the tetrahedron and the octahedron and the icosahedron are deltahedrons, but there are others. And what's particularly interesting are the convex ones. So I just remind you that convex means that, well, if A and B are on the surface, then the line segment AB, that line segment joining AB, lies inside the surface. So it turns out that the convex deltahedra, have the following possibilities for a number of faces. Well, they all have to be even. It's not hard to see that they're even, because if you count edges, then it's 3 times the number of faces is 2 times the number of edges, and so the number of faces has to be even. So F equals 4 is our tetrahedron, and then we have 6, 8, 10, 12, 14, 16, and 20. These are the only possible deltahedra.
Is there only one of each?
I think so, or essentially there is anyway. You'll notice that there's a conspicuous gap there. What happens to the deltahedron with 18 faces? Where is it? Okay, so let's do problem 12. Problem 12. A, show, no. If a 18-face deltahedron exists, how many vertices does it have? Secondly, what must the degrees of those vertices be? What must the degrees be? So, for example, by degree we mean the number of edges coming towards a vertex. So this vertex here, for example, has 1, 2, 3, 4, 5. That's degree 5. While this one here has degree 1, 2, 3, 4. It has a certain number of vertices of degree 5 and a certain number of degree 4. So I'm asking you, what must the degrees of the vertices be? And C, a star problem, again for those ambitious students. Prove that it doesn't exist. We're talking about the 18-face deltahedron.
Is that only for the convex one?
For the 18-face convex deltahedron, exactly. Okay, that might be a bit of a challenging exercise, I don't know. Okay, these are all very nice, but in some sense there's actually a much more interesting question than perhaps these. And that's what happens to the Platonic solids when you look at the situation in higher dimensions. What are the generalizations of the cube and the dodecahedron and so on? So the Platonic solids, or regular solids, in the sense of the Platonic solids, in higher dimensions, This was all worked out in the middle of the 19th century by a remarkable Swiss mathematician named Schafli. And I hope I'm spelling it right, and there might be a umlaut there somewhere. Okay. In the 1850s, perhaps, he figured out what are all the possibilities. So it turns out that of our various families, we have the tetrahedron, we have the cube, we have the octahedron, and then there's the icosahedron and the dodecahedron. These three have analogs in all dimensions. Okay? So I want to briefly describe these. It's reasonably easy to describe what they are. So how do you get the analog of a tetrahedron in general? Well, let me say, first of all, how does one think of a tetrahedron kind of symmetrically in ordinary space? One idea is to look at standard basis vectors. Take your favorite reference frame and consider the standard basis vectors and just join them up. If you do that, you get, well, that's usually called maybe a 2 simplex. That's obtained by joining it's actually in 3-dimensional space. And similarly, the tetrahedron can be thought of as what you get when you join the 4 basis vectors in 4-dimensional space. And so you can do exactly the same thing in higher dimensions. So you can get the n simplex, which is in a n plus 1, by taking the standard basis, well, E1, E2, E3, up to En plus 1, E1, E2, up to En plus 1. And considering essentially the convex hull of those, if you like, if you want something solid, just joining them all up. You're going to get the n simplex.
You join all of them to each other?
So, yeah, so each one is joined to every other one.
And 0?
No, 0 is not included. Only that's important. It's only the 3 basis vector ends themselves that are being included. We could also try to use 0, but it's more symmetrical if you do it this way. Otherwise, the tetrahedron is a little bit lopsided. What about a cube? Well, the right way of thinking about the cube, perhaps, is to think of it as a generalization of the square, where you're taking points of the form 1, 1, and 1, minus 1, and minus 1, minus 1, and minus 1, 1.
Sorry, going back to that, the 2 simplex in A3, that's, if you don't take 0, how do you get a tetrahedron?
You don't get a tetrahedron, you get a triangle. So this one's just a triangle.
So we'd have to get
So you'd have to go to 4 dimensions to get our ordinary tetrahedron. And the way I've drawn it, I've included sort of the interior too. If you want just what we're calling the polytope, you don't want to actually include the inside. You just take the boundary.
Oh, so that's what you mean when you refer to a polytope, not a polyhedron?
Yes, I think that's the usual kind of thing. The polytope it includes the interior.
Right, which one includes the interior?
The polytope.
You mean the surface and the
And its interior.
And polyhedron?
And polyhedron is the outside. That usage is not universal, I think, but it's probably reasonable. Okay, so how do we get a cube in 3 dimensions? Well, we could take the standard basis, and we could all look at all vectors of the form plus or minus 1, plus or minus 1, plus or minus 1. It's going to be 8 points. And it's going to be a cube which is centered at the origin. So square to cube, and now I think it's obvious how to keep going. in 4 dimensions, we would just look at the 16 points obtained by all 4 vectors with plus and minus 1s. That's called the hypercube. Okay, so maybe I'm running out of room here, but the hypercube would be in 4 dimensions. We'd be looking at all things with the form plus or minus 1, plus or minus 1, plus or minus 1, plus or minus 1. What about the octahedron? What's the right way of thinking about it? Well, let's go over here. The octahedron, you take the standard coordinate vectors again, and now you take vectors which are on either side, on unit vectors in both directions on each of the axes.
Plus or minus this.
So plus or minus the unit vectors. Okay. So there's a square there. So what we're doing here is we're taking things of the form plus or minus EI, where I goes from 1 to n, where EI are the standard basis vectors. So that gives us our hypercube, and here this is often called a orthoplex.
The tetrahedron was called a simplex.
A simplex. A simplex. Simplex, hypercube, orthoplex. It's the family that generalizes these 3 simplest of the Platonic solids.
And in the orthoplex, you don't join EI to its minus.
Well, it's not an adjacent, it's not an adjacent vertex. So you just join the nearest neighbor ones. This distance is less than that distance. So you join the ones that are closest to it.
So all but the opposite.
All but the opposite ones.
Yeah.
Yeah. And you can check that in general the hypercube and the orthoplex are dual in exactly the same way that the cube and the octahedron are dual. The number of vertices of this is the same as the number of faces of that, and the number of faces of that is the number of that. But there's also low, in between dimensional faces when you go to these higher dimensional things. It's not just vertices, edges, and faces, because there are faces of all intermediate dimensions. So these 3 families are in general in all dimensions. So naturally now the really interesting question is, what about the icosahedron and the dodecahedron? How do they generalize? And it's a very interesting answer that Schafli discovered. Remarkable piece of work. Which proves, I think, that we're probably living in the wrong dimension. Things are just a little bit more interesting in 4 dimensions. So the icosahedron and the dodecahedron only have analogs in 4 dimensions. And they're called the 120 cell and the 600 cell. 600 cell respectively. And to complete the story, and also there is something in 4 dimensions which doesn't have a direct analog in 3 dimensions. That's the 24 cell. That's kind of a new thing. And so this now exhausts the Platonic solids in all dimensions. In higher dimensions, there are no other regular objects other than these 3 infinite families. So the interesting things other than these 3 families are the icosahedron and dodecahedron in 3 dimensions, and these 3 objects in 4 dimensions. Okay, so let me explain them a little bit. So what is the 120 cell? Okay, it's an analog of the dodecahedron. So let me remind you how you might get the dodecahedron. One way of getting the dodecahedron is to start off with some pentagons. This is not a pentagon. I couldn't find a pentagon, but okay, pretend it's a pentagon. So if you have 3 pentagons, then they don't match up in the plane because they're not hexagons. Hexagons fit together, but they don't. But if you take the 3 pentagons and you put them together, it becomes rigid, and you get some curvature. And so if you just keep on attaching pentagons, somewhat miraculously, when you get around, it matches up to what you've been building on the other side. That's the point of the dodecahedron. Okay, it's some kind of miracle that happens. Okay, so you can do the same thing in 4 dimensions by starting with a dodecahedron instead of starting with a pentagon. Okay, so now if I had 4 dodecahedrons with me, and I was going to do this, but it was too much work to make them. You could see that I could attach 4 dodecahedrons together with enough room to spare at one vertex. I can put one there, this one, then another one, then a third one, and a fourth one together at the vertex, touching this vertex, and there will be a little bit of slack. There'll be some space between the dodecahedrons. Okay, so then if I glued one to here, and glued one here, and glued one here, then that'd be a lot like taking the 3 pentagons, which don't fit together with some slack here, and matching them up in 3-dimensional space, which you can't do in 2-dimensional space. So in 4-dimensional space, you could glue those 4 dodecahedrons together and look at it. And then you could say, well, here's an empty face which hasn't been glued. I'll keep on attaching dodecahedrons. So you end up building this big thing out of dodecahedrons as the building blocks, and you would start noticing that it kind of wraps around you. And when you put 120 of them together, it all would close up into some remarkable thing, which would be a 4-dimensional Platonic solid. That's the 120 cell. And the 600 cell, this 120 cell has 600 vertices, and its dual object is the 600 cell, made out of tetrahedrons.
Does Euler's formula work in 4 dimensions?
Well, a generalization of Euler's formula works for in 4 dimensions. For the 120 cell, I probably can't remember what the numbers are, but it's like this. The number of vertices is 600. Edges, let me leave that out. Faces, okay, there's 2-dimensional faces and 3-dimensional faces. The number of 3-dimensional faces, I've said, is 120. Okay, one of these, we can figure this out. Let's see. Okay, I'm not sure if I'm getting it. One of these is.
How many edges between the vertex?
I think one of them's 1,200. That might be 1,200. And okay, I should be able to figure this out now. 1320, 720. Okay, 720. That sounds right. Okay, I think those are the numbers. Okay, so it turns out that if you take chi equals v minus e plus f minus g, which is what you'd be first guess is what you would do, right? Yeah. That is the right object, the right number to think about, and it turns out it is 0 because, okay, it's 0. Okay. And it's an excellent exercise to show that the corresponding facts for the 4-dimensional simplex, hypercube, orthoplex also satisfy this, that the Euler characteristics are all 0. So, okay, good. Oh, the 24 cell. Yeah, the 24 cell is self-dual. These are dual. The 24 cell is self-dual. It's some kind of tetrahedral analog, but it's not really a tetrahedron. And Maybe if I have time later in the course, we talk about quaternions, I'll explain how to think about that using quaternions, but I'm not sure if I'll get to that. Okay, so graphs. What is a graph? Well, okay, so very quickly, it's got some vertices, which are dots. And it's got some edges, which connect the vertices. And sometimes it can have loops, so that's called a loop. An edge going from a vertex to itself. Or it can have multiple edges from one vertex to another. That's sometimes called parallel edges. Loops and parallel edges are not always what we want to talk about, so a simple graph, that means no loops and no parallel edges. And often when we say graph, we mean simple graph. Another convention that we often use is we assume the graphs are connected. Okay, there's a graph there. Let's make sure we know what the vertices are. There. Okay, so let's count vertices, edges, and faces. So this one here has vertices 1, 2, 3, 4, 5. Edges. Well, that's 1, 2, 3, 4, 5, 6, 7, 8. Faces. Let's see, that's a face. 1, 2, 3, 4. And then we generally want to include the outside as well. Okay, so we're going to include the outside as well. So 5. Outside included. And lo and behold, V minus E plus F equals 2. This is a more general situation than the situation on a sphere, because we're also allowing things like this that we didn't allow before with polyhedra. We're also allowing loops and parallel edges. So it's a bit more general than it used to be. So here's a theorem that for a planar graph, that's, in other words, one that you can draw on the board just like I've done.
No crossing over?
Yeah, no crossing over. So, because if we crossed over, then it's painful to count what exactly are the faces. So it separates the plane nicely into pieces that we can count, the faces. So for a planar graph, V minus E plus F equals 2. Okay, so here's a proof. Take an edge. If it is a loop, remove it. Then E goes to E minus 1, and F goes to F minus 1. And so we are still happy. The combination V minus E plus F equals, well, V minus E plus F has not changed. So here's a loop. So according to my instruction, I should just get rid of it. Okay, I will. Okay, now we have a slightly simpler graph. Okay. Now, if it is joining two vertices, shrink it. So the vertices coincide. So that means that the edges have been reduced by 1, and the vertices have also been reduced by 1.
Wait, so we're happy to create parallel edges in that case?
Hang on, let's have a look. So let's shrink. Let's take this edge here. Yeah, parallel edges. We started with not necessarily a simple graph. We allowed loops and parallel edges. So let me illustrate here. Let's suppose we pick this edge right here. Okay, I'm going to shrink that, just like imagine elastic band and pulling it together. So now I have the triangle still before, that thing coming up. Okay, now that's shrunk to there, and now these two are there. Okay, so have the number of faces stayed the same? So I guess that one sort of became that one, I guess. And that one became that one, and that one became still the outside. Okay, so continue until, well, each edge is going to disappear or be shrunk. So at the end, you're not going to have any edges. So continue until a single vertex remains. We can't have two or more vertices because we're assuming the thing was connected at the beginning. It all stays connected. So at this point, now we have v equals 1, e equals 0, and f equals 1, because it's only the one outside face. And so v minus e plus f equals 2. Too easy, I think. Seems like cheating. Okay, so we'll stop there. So next time we're going to talk more about this formula and various applications of it. So I'll see you then.